Today we'll cover section 13.2 on measures of dispersion. In the previous section we studied the mean, median, and mode. Those are measures of central tendency, in other words, locations around which the data tends to cluster. For example, suppose we plot a small data set. Say it looks like that. And then a second one. It looks the same, but it's in a different location. And yet a third one. If you plot them all together, you can see that the data sets basically look the same. They've just been shifted. In other words, they have different means, medians, and modes, but each is equally spread out or dispersed. That's what we mean by dispersion. Each of those three data sets is equally dispersed. That's what leads us to the study of measures of variation or dispersion of data, as a contrast to just a measure of location, which we studied in the previous section. These measures will tell us in some sense just how much the data are either spread out or packed in together. The first and simplest measure of variation is called the range. The range of a data set is simply the difference between the largest and smallest data points. So the range is just a maximum value minus a minimum value. It's a relatively crude measure of the spread of data set because it doesn't say anything about the values in between the minimum and maximum values. Here's an example that's sort of aged. It's been in my slides for quite a long time, so the information may be out of date, but the point is the same. This is a list of the heights in inches of 4 different people. At least at the time, the tallest person in the world, the shortest person, and 2 other people, including LeBron James and LaDainian Tomlinson. In any case, the range of that data set would simply be the largest number, the maximum, minus the smallest number, the minimum. In this case, that would be 102 minus 26, which happens to be 76 inches. And in case you're interested, that's about 6 feet 4 inches. Another measure of variation of data in a data set is called the standard deviation. This is the formula of the standard deviation. If you want to find the standard deviation, we use a small s of a sample of n values. You use this formula. Notice the sigma in the formula is our notation we talked about earlier that just means to sum things up. So you're going to be finding the mean because you see an x bar. You're going to subtract each value x from the mean, square that result, then sum them all up, divide by 1 less than the number of values, and take the square root of that result. The best way to do this is in a table. The numbers are not going to get large, so it's easy to do. So suppose we take this data set, 16, 14, 12, 21, and 22, and illustrate how easy this is. You've got to have the mean before you can go any further, and if you calculate that like we did earlier, you simply add them up and divide by 5, since there are 5 of them, you'll get 17. I'm not going back through that, but you should get 17. From there, if you build a table, your first column are just your data values, the x's we'll call them, 16, 14, 12, 21, and 22. Then you want a column for the deviation of those values from the mean. In other words, if the mean is 17, how far is each of those values from the mean? So you take the value, subtract the mean. So if you take the first value of 16 and subtract the mean of 17, you get a deviation from the mean of -1. Do the same for the second value, you get a deviation of -3. If you take 17 away from the third value, you get 12 minus 17 is -5, and all the way down the column. 21 minus 17 is 4, 22 minus 17 is 5. Those are the deviations from the mean. Notice in the formula above, you're going to have to square those. So you want a column that just squares all those numbers. So -1 squared is 1, -3 squared is 9, -5 squared is 25, 4 squared is 16, and 5 squared is 25. And then the sigma comes into play, which tells you to add them up. So using this table model, you're going to sum all the values in the last column. And that's going to be the numerator under the square root for the standard deviation. So adding up those numbers, you get 76. So that goes in the numerator. There are 5 values, 16, 14, 12, 21, and 22, so you divide by 5 minus 1, which is 4. So the standard deviation is the square root of the fraction 76/4. 76/4 turns out to be 19, so you end up with the square root of 19. And if we want to round that to say 2 decimal places, you'll end up being 4.36. So the standard deviation rounded to 2 decimal places is 4.36. It's a very straightforward procedure. We'll never let the numbers get very large or numerous, so it's easy to do. Might be a good time to introduce another term called the variance, in this case the sample variance. The variance is simply the square of the standard deviation. So you still have to calculate the standard deviation and then you just square it. So in this case you get 4.36 squared. That will be the variance. Let's do another example. Suppose a company hired 6 interns. After 4 months, their work records show the number of work days missed for each worker. One worker missed 0 days, another missed 2 days, another 1 day, 4 days, 3 days, and 2 days. And the instructions here are to find the mean, sample standard deviation, and the sample variance of this data set and round the final answer to 2 decimal places. So let's calculate the mean. We've done that several times now. You just add up the numbers. 0 plus 2 plus 1 plus 4 plus 2 plus 3 adds up to 12. There are 6 numbers. 12 divided by 6 is 2. So the mean x bar is equal to 2. Now you're going to use the formula. Remember, in the formula, to get the numerator, under the square root, you want to build this table. Put the values in the first column, then measure their deviations from the mean. So the mean is 2, so you take 2 away from every number in that first column. 0 minus 2, negative 2. 2 minus 2 is 0. 1 minus 2, minus 1. 4 minus 2 is 2. 2 minus 2 is 0. 3 minus 2 is 1. And then the third column is the square of those numbers. You square each of the numbers in the middle column and then add them up. So you get 4 plus 0 plus 1 plus 4 plus 9. That comes out to 10. That's the numerator. Remember, that's the numerator under the square root is 10. This time there are 6 data points. So it's 6 minus 1 is 5. 10 divided by 5 is 2. So it's the square root of 2. It says to round to 2 decimal places. That would be about 1.41. The sample variance is simply the square of the standard deviation, so you square 1.41, and if you round it off to 2 decimal places, you'll get 2.00. Now, this has nothing to do with your ability to do these problems, but I do feel that I should try to explain a little bit about what this standard deviation really is. And I'm going to give it a shot, but understanding what I'm going to say from here out really doesn't affect your ability to do the problems. I'm just trying to add a little bit more to your understanding. So let's give it a shot. Suppose the length that I put up here on the screen represents the difference between 2 values. And what if each of the line segments I've displayed down here in the lower left quadrant is 1 standard deviation in length? If I take one of those things and then another and then another and then another and stretch them along the length of that wider segment, it turns out it takes 4 of them to equal the length of that one wider bar. So what I could say is that blue bar, that wider bar, is 4 standard deviations long. But what if the bars for the standard deviations were really longer? What if on the right quadrant, what if those bars represented 1 standard deviation in length? What if I stretch those bars out? Well, it takes only 3 of those. So the wider bar is 3 standard deviations long if the standard deviation is the length of one of the bars on the right, but the length of the wider bar is 4 standard deviations long if the standard deviation is the length of the bars on the lower left quadrant. So in effect, when we calculate a standard deviation, we're computing the length of our measuring stick. If the standard deviation is really small, it'll take several standard deviations to span a certain distance. If the standard deviation is larger, it takes fewer of them. Now, I don't know if that helps or not. It has no bearing on whether you can do the calculations or not, but I do hope that it gives you some little bit of more understanding in what a standard deviation is. It's sort of the length of our measuring stick.